All right, we introduced the idea of chemical systems at equilibrium. This is like the juggling back and forth, or like people going up and down an escalator. An exceedingly large number of biochemical reactions are equilibrium reactions, where if the external conditions change, the reaction is going to change to respond. And this is in chemistry called Le Chatelier's principle, where if a chemical system is at equilibrium, and again, this equilibrium is where reactions tend to go. If we sort of leave things alone and time is passing and things aren't changing, a chemical system that can find equilibrium will tend to get there. If we disturb it or stress it out, and chemically speaking, this could be from like eating a big meal or being in a warm environment or something like that, the system is going to react to counteract that disturbance and relieve that stress. It's going to find a new equilibrium that is another new, most stable way for the reaction to be. And this gives our body an ability to respond to stresses. When our body feels something different, it's able to recalibrate and still thrive. And this is really important because biologically speaking, resources don't just come in slowly and steadily and are guaranteed. We have gluts of resource that's available, and our chemical system's ability to adjust to that and make the most of it really is very much related to the ability to adjust back to a disturbance, to equilibrium. And so, we'll get to sort of these in a minute. For healthcare, it's really important to know about this because of the connection to biochemistry. It may not seem like a very healthcare related topic, but understanding the fundamentals of equilibrium reactions really is an important part of this course. And so some of the disturbances we can see: concentration changes, temperature changes. This is pretty much the big ones that we want to think about. And when I mentioned like a big meal and how your body can adjust to that, or a lot of sugar being introduced to the system, say, that's really a concentration change. If you have a chemical reaction that depends on sugar and sugar is introduced, that means that there's more sugar there. It's happening in an aqueous environment. That's a concentration change. What about for this reaction that we looked at before? CO2 and water makes H+, namely here. This is our acidity unit that we're going to look at and explore later. Well, if CO2 increases, like in hypoventilation, equilibrium shifts right. That means that there is going to be more H+ produced in the blood because there's more CO2 present. And this is because there's more reactant. The reaction says, hey, that's too much reactant. Now I've got more reactant than I want. How can I adjust? I shift to the right. And the observation of this change is that there's more H+ and a drop in pH, the blood becomes acidic. For the reverse, if CO2 decreases, the equilibrium is going to shift less. There's not enough reactant, right? The reactant has been removed. In this case, the reaction says, hey, we don't have enough on the left. We have to shift to the left in order to make more of the reactants. This is what an equilibrium reaction is able to do and what it will do when something changes. What about temperature? So this is going to depend on whether the reaction is endothermic or exothermic. If it's endothermic, heat is pretty much like a reactant, and we kind of can view it the same way. If we increase temperature, that's like adding heat. There's more reactants, and it's going to shift right in a hot environment. If we decrease temperature, the system is going to shift to the left in order to produce more heat. That's like removing heat, and now the reaction needs to shift left to compensate. Again, when we make a change, we look at a reaction and say, well, what is this reaction missing? Or what does this reaction have too much of? Depending on how you frame that, you'll be able to interpret the change. And it should be the same thing, right? Whether it's too much product or too little reactants, that's the same thing. It needs to shift to the left. It's just perspective. Exothermic reactions, the opposite. Heat is a product in an exothermic reaction. Increasing temperature means there's too much product, it has to shift left. Decreasing the temperature means not enough product, it's going to shift right. And these terms, shift left, shift right, are used very commonly in chemistry. Observing the change and predicting the change is what we're looking at here in Le Chatelier's principle in our last video. Oxygen to hemoglobin, this is an exothermic reaction, and so here is that reaction, and because this is classified as exothermic, it's going to release heat. When temperature increases, this means we have excess heat. Heat is a product, and so it's going to shift to the left. Oxygen is a reactant in this case, so shifting to a left means that it's going to release more oxygen when the body's temperature increases. If the body temperature decreases, equilibrium is going to shift to the right. It's going to bind oxygen more tightly, which is going to cause oxygen and the heme to be more associated. The final way, and this isn't quite as applicable in healthcare, but definitely is in terms of engineering and just general, chemical reactions. When pressure increases, the equilibrium is going to shift to where there's the smallest number of gas. It basically, if it's under pressure, it wants to shrink or it wants to expand. And so in this case, where we have a reaction that features 4 moles of gas on the left and only 2 on the right, increasing pressure means it wants to shift to the right. It makes itself smaller in order to alleviate those pressure changes. If we decrease pressure, now it's feeling the ability to expand and it wants to do so. It'll shift to the left in order to adjust for that decrease in pressure. And this is really an important thing to consider for Le Chatelier's principle. However, when it comes to healthcare, our bodies tend to be kind of a constant pressure system. This won't come up as much as the effects of changing concentration, meaning quantity of reactants or products, and temperature change.